Hi guys, my name is Fiyaz Ahmed, and in this lecture we will solve some examples on Routh Hurwitz criterion. We will take example of a unity feedback system where we have inserted a proportional controller with gain k, and we have this open loop transfer function of the system s plus 1 or s into s minus 1 into s plus 6. This is placed in a unity feedback formation. We are interested in determining the range of k which will make the system stable. So let's go for t of s, which is the closed loop transfer function. We will solve for t of s, and we will write the by using the feedback formula, which is kg of s 1 over 1 plus kg of s k, and this is g of s divided by 1 plus kg of s. If we further solve it, this will become k is plus 1 or s into s minus 1, s into s plus 6, k into s plus 1. So this is now the characteristic equation of the system. We'll be interested in this characteristic equation. Okay, now if we take that characteristic equation, s into s minus 1, s plus 6 plus k into s plus 1, we solve it. We can write it in this form. We insert these values in the root array with the s power cube, s square, s1, s0, and then we write its coefficient 1, k minus 6, and the left out coefficient is 5, k here, and then solving for the using the determinant formula, we take these terms and solve it like 1 into k minus 5 into k minus 6 divided by 5 with minus sign. So this will be that thing. If we solve it, this is k minus 5k plus 30, so 30 is going to be 4k minus 30 by 5 all the way, and then if you solve further, you will get this thing. And k, the first column is important for us, this one. We are interested in, since this is positive, we know that this number should also be positive, and this k should also be positive. If this k is positive, this simply means then k should be greater than 0, and for this number to be positive, we say that 4k minus 30 over 5 should be greater than 0, which simply means that k should be greater than 7.5, this condition. Now we have this condition, we have these two conditions now. If we look at this condition, k greater than 7.5, it includes this condition, so we are taking k greater than 7.5. If we take k greater than 7.5, this system is going to be stable all the time, so all the poles will be in the left half plane and there will be no pole left in the right half plane. However, for k equal to 7.5, what happens? If k is equal to 7.5, this value is becoming 0. Since if you put k 7.5 here, this is going to be 30, and 30 minus 30 is 0, and this will become a 0 row. And remember that case where we had a 0 row, we would form a auxiliary polynomial, which will be this one, s square, f5 square plus k, and we will take derivative and then solve it and things like that. So what was the case when we had a 0 row? We used to take auxiliary polynomial, and that auxiliary polynomial was the order of that auxiliary polynomial would determine how many poles would be located on the imaginary axis. Since in this case, if this row is 0, we have auxiliary polynomial of order of s square, so we'll have two imaginary poles on the imaginary axis. But in this case, we will not take k equal to 7.5. We will always take k greater than 7.5, so that we have poles in the left half plane. Now we have plotted the auxiliary polynomial here. For k equal to 7.5, this situation is undamped. You can see that these oscillations are undamped, sustained oscillations, a sine wave form. However, if we take k greater than 7.5, that is 13, we have some overshoot, and then the oscillations are decaying and reaching certain final value, but it takes normally longer time to settle down. And if we take k even larger, equal to 25, this overshoot is decreasing and the system is settling down quickly. But these are the dynamics of the auxiliary polynomial. Remember that we had the system whose order was third, so in this case one pole is in the left half plane and two poles will be in the on the imaginary axis if we take k equal to 7.5. However, if we take k greater than 7.5, all the three poles will be in the left half plane. Let's look at another example. We can see that we have a system where we have the controller parameters are now 2, k and ki. This is now pi controller, which is proportional integral control, and we have this g of s, and it is also in the unity feedback formation. So if we take the t of s, this is now d of s, because this is the transfer function of the controller, or you can say c of s. So we say d of s, g of s, this is d of s, this is g of s, and this is 1 plus d of s, g of s. We will take this characteristic equation, which if we solve it, this is the characteristic equation now, what the values for k and ki should be selected so that the system is stable. Now we have this characteristic equation, we write the Routh table. For it, we make the Routh table. First coefficient comes here, the alternate coefficient goes here, and then 3 goes here and ki goes here. If we will solve this table, and this is very straightforward, since we will take the determinant and then divide by 3, we get this thing, and then we determinant of 0 0 and we get this 0, and then we take the determinant of these two elements, this and this, this and this, we get this value, and so on. Now we have two parameters, one is k, the other one is ki. We need to find the stable ranges of these two parameters. Now we want that this row should have no sign changes. Since this is positive, this is positive, this element should also be positive, this should be positive, so ki should be positive, and in order to be, and this element should also be positive. Okay, how do we get this? We equate this equal greater than 0 and we solve for it. For k, we say that k is greater than ki minus 6 over 3. So if ki is positive, if we take some value, let's say if we take ki equal to 6, if we put 6 here, it will become 0, k greater than 0. So that means if k is 0, this equation is going to be 0, because k is 0 and ki is 6, so this is going to be 0. This row is going to become 0 0 0, so we'll have an auxiliary polynomial of second degree, and we'll have two imaginary poles. However, if we take k greater than 6, like if ki is greater than 6, we will have this thing, we'll have k greater than 0, this condition will be valid, ki is still greater than 0, and we'll have k greater than this thing, so we'll be putting, let's say, 7 minus 6, 1 over 3, we will put k greater than 1.1 over 3, that means 0.33, so still we will have both the conditions will be satisfied, and there will be no sign changes, and we'll have a stable system. So this is for today's lecture, and I hope that you will have liked it. If you have any questions, please put them in the comment section or just write to me in the WhatsApp group. Thank you very much.